Ever wondered what $10 billion could get you? Well, for starters, if you're the kind who wants fancy living, you could literally buy the White House 25 times over, since it's valued at about $400 million. If you like traveling, there's always a chance you could pick up a mere 20 private jets. That'll cost you $500 million each. But if you're really into exclusivity, you can purchase at least 10 private islands. $10 billion can get you a lot, including the James Webb Telescope. But so far, the observatory has outvalued its cost price by a whole lot, giving us some of the most exquisite views of the cosmos that we've ever seen before. These images are so clear they might just be breaking cosmology as we know it. So what have astronomers found, and what are their implications? Harvard University's Rohan Naidu was the first to find the galaxy that nearly busted cosmology. When he looked through early images from the James Webb Space Telescope late one night in July 2022, something caught his attention. He found an object that was incredibly large and dated back to just 300 million years after the Big Bang. This was older than any galaxy that had ever been seen before. Naidu started working right away after exchanging excited messages with one of his collaborators. They published a paper a few days later on the targeted galaxy, which was called Glass Z13. This got a globe full of space-loving enthusiasts talking. The tremendous discovery of this galaxy just weeks into JWST's full operations was the stuff of legends. The largest, most powerful observatory ever launched from Earth, the JWST, was custom-built to inspire our understanding of the universe. The telescope is 1.5 million kilometers away from Earth and is chilled to near absolute 0 degrees by a sunshade that is about the size of a tennis court. The giant mirror and sensitive instruments were designed to see details of an early universe that have never been seen before. This is a barely examined time period, no more than a few hundred million years after the Big Bang itself, in which the very first stars and galaxies blended. The physics of dark matter, dark energy, starlight, gas, and dust are all variables that affect how this process unfolded. With JWST, cosmologists can test their knowledge of all these underlying phenomena by seeing galaxies from then, either confirming the validity of their best consensus models or showing gaps in understanding that could lead to new discoveries. It was supposed to take time for JWST to find the first galaxies. Initial projections said that the first galaxies would be so small and faint that JWST would only be able to find a few interesting candidates in its first investigations. Instead of waiting for the scientists to release the first images from the telescope, astronomers like Naidu started finding galaxies in the images that were bigger, older, and brighter than anyone had expected. There was a lot of competition to be the first to discover an earliest known galaxy. With each day, it seemed like another group claimed to have found one. Charlotte Mason, an astrophysicist at the University of Copenhagen, described the situation as, "Everyone was freaking out. We really weren't expecting this." Since JWST found early galaxies that were more mature than expected, theorists and observers have been trying to figure out how to explain them. Could the large number of bright, big galaxies at the beginning of time be an illusion? Could standard cosmological models explain them if they're real? They might have been the first hints that the universe is more complex than we had thought. At stake is our understanding of how the orderly universe we've come to know of emerged from primordial chaos. JWST could change the story of how the universe began, which would affect not only distant galaxies and eras, but also our own existence here in the Milky Way. JWST scientist Mark McCaughrean, a senior advisor for science and exploration at the European Space Agency, said in a statement, "You build these machines not to conform the paradigm, but to break it. You just don't know how it will break." The Hubble telescope spotted the most distant galaxy called GNZ11 at a redshift of 11 in 2015, thanks to a 2009 upgrade to the telescope. A redshift of 11 is about 400 million years old. This is close to the time when it was thought that galaxies started to form. But the galaxy that Naidu found, Glass Z13, is a redshift of 13, which is 70 million years farther back in time. Researchers use redshift estimates from simple brightness-based measurements to get quick results. These are easier to get but less precise than direct redshift measurements, which require a healthy mensuration period. However, the simplified technique can be accurate, and here it suggested a galaxy that was surprisingly bright and big, already containing the mass of 1 billion stars, just a few hundred times less than that of the Milky Way, despite our own galaxy being billions of years more mature. Tommaso Triu, an astronomer at the University of California, Los Angeles, and the lead on Glass, commented on this saying, "This was beyond our most optimistic expectations." The record did not last very long. Dozens of galaxy prospects from 180 million years after the Big Bang appeared, with estimated redshifts as high as 20, and some with disk-like structures that weren't expected to appear so early in the history of the universe. Another team found evidence for galaxies as big as our Milky Way at a redshift of 10, less than 500 million years after the Big Bang. It was surprising that these huge structures were appearing so quickly, because the standard model of how the universe evolved, set by cosmologists, doesn't expect them to appear so soon. Lambda CDM, or LCDM for short, is the model scientists use to best estimate the properties of dark energy and dark matter, which together make up most of the large-scale structures in the universe. Michael Boylan-Colchin, a cosmologist at the University of Texas at Austin, commented on this situation saying, "Even if you took everything that was available to form stars and snapped your fingers instantaneously, you still wouldn't be able to get that big that early. It would be a real revolution." You might be asking at this point, well, most of what you said is great, I'm sure, but where is the real issue here? I'm glad you asked, but before we get to the real issue here, we need to get a quick refresher about the Big Bang. So, right after the Big Bang, our universe was a very hot and dense soup of primordial particles. As the universe expanded and cooled, the light elements began to form. 400,000 years later, the universe was cold enough for the first atoms to form. The first stars are said to have appeared about 100 million years after the universe was formed. These giant fireballs were different from modern-day stars because they were made of mostly hydrogen and helium and didn't have heavier elements like current stars do. These first suns were bigger and brighter than today's stars and formed in proto-galaxies, groups of gas that stuck to huge dark matter platforms. Gravity caused these proto-galaxies to interact with each other, and they eventually merged to make bigger galaxies. This process of becoming, which started with the early universe's chaos and ended with the more orderly universe we know today, is thought to have taken about 1 billion years, which brings us to the actual problem here. This model is challenged by the discovery of bright galaxies in the early universe. Stacy McGough, a cosmologist at Case Western Reserve University in Ohio, comments, "We should see lots of these little proto-galactic fragments that have not yet merged to make a big galaxy. Instead, we're seeing a few things that are already big galaxies." It is possible that some of these galaxies are not real because they are shrouded in dust that makes them look dimmer, but follow-up observations of Glass Z13 in August by the Atacama Large Millimeter Array, or ALMA, in Chile suggest that this candidate is legit because ALMA did not see a lot of dust. Yet the lack of dust meant that ALMA had a hard time seeing the galaxy at all. This shows how difficult it is for telescopes to match JWST's pace to confirm its most exciting observations. The most surprising idea is that the standard LCDM cosmological model is wrong and needs to be changed. Cosmologist Boylan Colchin says these results are very surprising and hard to get in our standard model of cosmology, and it's probably not a small change. We'd have to go back to the drawing board. Some specialists think that large-scale fluctuations in gravity can explain dark matter without it actually existing, which we've come to know as modified Newtonian dynamics, or MOND. The observations made by the Webb could support the theory. One idea is that the galaxies in the early universe might have had little or no dust, making them look brighter. This scenario could make it harder to figure out the true masses of the galaxies, and could maybe also explain why ALMA had a hard time finding Glass Z13. Andrea Ferrara, an astronomer at the Scuola Normale Superiore University in Italy, who has proposed such a possibility, commented on this saying, "It could be that supernovae didn't have enough time to produce the dust, or maybe in the initial phases of galaxy formation, the dust is expelled from the galaxies." On the flip side, Mason and her colleagues suggest that the JWST may only be seeing the brightest young galaxies so far, since they should be the easiest to spot, saying maybe there's something happening in the early universe that means it's easier for some galaxies to form stars. David Spergel, a famous theoretical astrophysicist who is currently the president of the Simons Foundation in New York, agrees, saying, "I think that what we're seeing is that high-mass star formation is very efficient in the early universe. The gas pressures are higher, the temperatures are higher. That has an enormous impact on the environment for star formation. We might be seeing a signature of magnetic fields emerging very early in the universe's history." Maybe magnetic fields were even more important in the early universe than we thought, and played a big part in getting material moving to start the process of making stars. When the first data from JWST started coming through, astronomers were ready to receive it. The rapid flow of scientific papers was not a fluke. They were waiting for it. Many people chose to publish their scientific papers on Arxiv instead of using the traditional peer review process, which can take months. Arxiv is a website where people can upload their scientific papers after a minimal review by the moderators, but before a more thorough peer review. Today, peer review is often done in near real time for everyone to see on Twitter and other social media platforms. The action caught many off guard. This made scientific results easy to share and talk about, but some people think that this came at a cost. Problems with the JWST may have affected results. Researchers from the University of Manchester in the UK found that one galaxy's redshift could be changed from 20.4 to 0.7. Even though these issues won't get rid of all of JWST's high redshift galaxies, there are still a lot of them. Now that astronomers know that JWST can see these high redshift galaxy candidates, they are racing to use JWST to look at them again. Many groups want to use JWST to look at these galaxies, and most of them want to look at them more closely. More programs are coming out that will look for early galaxies, like Cosmos Webb, which will see a bigger area for hundreds of hours and find a lot more early galaxies. Future proposals might use the explosive deaths of supersized first stars in supernovae as markers for the existence of first proto-galaxies. There are some estimates that the JWST could see a redshift of 26, just 120 million years after the Big Bang. The growing list of high redshift candidates will be followed by a lot of work. JWST has been the start of an amazing time for science. Even with all the uncertainties, astronomers have been excited by the quick spread of new ideas as they are made and shared. It is time to re-examine our understanding of the beginning of things, if we can really believe what we are seeing. So what do you think? What is the solution to this revolutionary discovery? And what more will the James Webb Telescope find? Let us know in the comments below, and as always, thanks for watching Space Age.